In this video, we'll pick up where we left off, and I'll actually start on problem number 81 at this point. Since this is an absolute value function, we should go back to our basic definition of absolute value. And recall that an absolute value function implies a piecewise function, absolute value of x minus 1. When x minus 1 is less than or equal to 0, that will equal the opposite of the quantity that's in between the absolute value bars. But the x minus 1 less than or equal to 0, that can be simplified to read x is less than or equal to 1. So I'll just use that definition. And when x is greater than 1, then that will be whatever is the expression inside the absolute value bars. So we're going to use this piecewise definition as we test the left and right side limit using the alternate form of the derivative. So what we want to do is test the limit of that expression, not the limit of the original function, but the limit of f of x minus f of 1 in this case over x minus 1 as we approach from the left and as we approach from the right. And we'll see that it has different definitions, and we want to see whether or not those two definitions lead to the same limit on both sides. So I set up the basic formula. I want to test from the left, and in this case a is going to equal 1. And f of x here, since we're approaching 1 from the left, then we're going to be on the top branch of the piecewise function because all of our values will be less than 1 or equal to 1. So f of x in that case is negative quantity x minus 1. And since a is 1, I would have f of 1 would be negative, first of all, minus, then the quantity negative 1 minus 1, since x is equal to 1. But that whole piece on the right is all going to be 0. And so we're not going to really worry about it. Now this whole expression is over x minus 1 since a is 1. And because x minus 1 factors cancel also, we're left with a value of negative 1. And we can see that clearly from the graph that the slope of the line is equal to negative 1. Now from the right, we have the limit as x approaches a from the right. Well, I'm going to make that for space sake. I'm going to change that to x approaches 1 from the right. And you can see back over here at the piecewise function then that when we are approaching 1 from the right, all of our x values are greater than 1. And so we'll be using the second branch of that piecewise definition. So f of x in this case will just be x minus 1. So it's f of x minus f of 1, and f of 1 would just be x minus 1, or 1 minus 1, because x is equal to 1. And that is all over x minus 1. Well, the right side of the numerator is all going to be 0. And then the x minus 1 factors are going to cancel. Remember that when they cancel, they leave 1 and not 0. And so in that case, the limit as you approach from the right is a 1. So you can see that the two limits, the left and the right side, do not agree. They both exist, but they have different values. And because of that, there is not going to be a smooth transition from the left side to the right side at x equals 1. And we can see that clearly in the graph. As we approach 1 from the left, we have a negative slope, and as we approach 1 from the right, we have a positive slope, and constant, not just positive, but a positive and constant slope from the left or from the right. I'm sorry, from the left it would be a negative constant slope, from the right it's a positive constant slope. And what that tells us is that we end up with a sharp turn. So when they disagree, there will be a sharp turn at that point, and so this function is not differentiable at x equals 1.